Welcome. Today we're going to talk about contour integrals in the complex plane. So this is really the main event. This is what we've been working up towards for a while now. So let's talk about what a contour integral is. We're going to talk about this now. We have this idea of what a contour is, right? This is a contour. And it's just some curve in the complex plane, like that, x and y, right, IY. All right, and it starts at a point, at some point, and it ends at some point. And we typically parameterize this contour as z of t, some function that t starts somewhere around a and then ends at b. So that'll be t equals a, and that'll be t equals b. Okay, so that's the idea here. And now we want to write down the contour integral, so I'll call it I, is equal to this statement, integral over the contour C of some function f of z dz. All right, so let's just stop for a minute and understand what we mean by this symbol. This is what I would call an abstract symbol for integration. And what I mean by that is that it expresses what we want to do, but it's not explicit or constructive. It's not a constructive expression. It's not a constructive expression used to compute the actual value, the value I. Okay, so I is some complex number, and it's going to be this integral. And the idea here is, and let's see these different parts here. C again is this contour that might be defined by this function z. But we need to know more about what dz is. Okay, and of course this function f of z, which is some interesting function here. All right, so let's talk about that a little bit more in detail. So again, we have this contour, and I can draw it like that. And if I take a point on this and another point on that, and I see this is z of t, and at some later point we're traveling along there, and we get to z of t plus delta t. We're going to keep doing that, breaking it up into little delta t pieces, so on and so forth, like that. Until we get to the end, right? So what we mean by this symbol then, so we have this z of t, and that's equal, that generates the contour, and that's for t between a and b. Okay, so this symbol f of z dz, we have to know what dz means. So what I can do then is actually write, well, what we really want to do is sample this function. We want to take f of z and sample it at points z of t, okay? But then we're going to multiply it by some delta z, right? So let's rewrite this. I'm going to rewrite this in this approximate form. So this will be I equals 1, sorry, it'll be I equals 1, I equals 2, 3, 4. We're going to break it up into these little pieces here. So we're going to sum together a bunch of complex numbers, I equals 1 all the way to n, however many of these there are. And then we're going to have each one of these be a zi. So that's going to be f at zi right there. Okay. Or actually, we can write it a little bit more precisely, z of ti. That'd be a better way to write it. Okay. And then we're going to times it by some delta z. Okay. So delta z is going to be, I'm going to blow this up here a little bit. I'll blow this up big. Like that. This will be the point there to there, and again, that's this contour that's going like that. So delta z is going to be, if this is z at t I, and that's z at ti plus delta t, or otherwise we would call this t I plus 1, okay? Then delta z is this vector that lies between the two. So we can say delta z then is going to be equal to z at ti plus delta t minus z at ti. Okay, and that'll be delta zi. So that's just indexing. So we could have, of course, different delta z's at different times. All right. One way to write this, as long as delta t is small, we can write this as actually dz dt evaluated at zi, or sorry, I should write that, ti times some very small delta t. All right, so that's a good approximation. I call this oops. This is, of course, the linear approximation, which becomes accurate as delta t goes to 0. I shouldn't say it becomes accurate. It becomes more accurate as delta t goes to 0. And in fact, eventually, of course, if I divide this through here, this becomes a perfect. So as long as our curve is differentiable, this becomes a perfect expression. All right, so we can write that now as follows. Then that means that our integral, we can put that down there, becomes I equals 1 all the way to n for whatever number of values, little segments that we have that define, we've sort of broken up our curve into, of f of z of ti times dz dt evaluated at ti delta t. And of course, as we take delta t going to 0, we get this integral. We can say that this whole thing here then limits to this integral a to b of f of z of t, z prime of t dt. Okay. So what we're saying here then is this is the constructive version of that. Okay. So this is our constructive formula. So that's an integral from a to b. So I'm going to call that then the constructive integral. And I'm going to call, this is of course a more efficient, this is sort of a symbol. Okay, so this is of course a much more compact notation. It symbolizes what we want to do, and it's a more compact way to write it. But this is an explicit expression that we can actually perform a computation on. So this is our definition of a contour integral. All right. So what it takes to create a constructive integral here is, of course, parameterizing our curve. We need to be able to find how to parameterize our contour. And once we parameterize that contour, then we can compute this constructive integral. All right, so let's go now do some examples of such. Okay, I'm going to take a first example. Will be f of z is equal to z bar. Okay, and again, z is equal to x plus I y. All right, and then along with this, we have the curve, and the curve is going to be starting down here, and it'll be the half circle. And it's a unit circle, okay? So it'll be the half unit circle. All right, so let's see, we have to So we have to actually, so again, what we want to write down is, we write down this symbol, f of z dz, okay? But now we have to find a constructive way to put this all together. So first of all, we need to find z of t. Z of t is going to be equal to e to the I t. All right, so e to the I t, and then we have to have limits on our integral, so we're going to start at, we're going to start at negative pi over 2. That puts us down here at the start, okay? And we're going to go all the way up to pi over 2, okay? And then what's our z prime? Z prime of t, we can write that down as I e to the I t. Okay, so let's put this together. We're going to constructively write this then as, negative pi over 2 to pi over 2. And then we have to put our, so we also, let's just over here in our margin over here, let's write a few more things. We're going to evaluate f of z at these values. So f of e to the I t is e to the I t complex conjugate, which turns out to be e to the negative I t. Okay, so we put that down there, right? Again, the formula is a to b f of z of t, z prime of t dt. Okay, so we have to put this in its place. This will be e to the negative I t. Right, and the next thing we have to do is, so that's this part right there. And the next part we have to put z prime in there, and we have that put right in there, e to the I times e to the I t, and then finally dt. Okay, so we can rewrite this again. And we see that these two cancel with each other because this is a negative exponent and that's a positive. So we're just left with I dt. Okay, we can integrate this. This is I t evaluated at negative pi over 2 to pi over 2, which is simply I pi. Okay, so let's stop now and just cover one thing about contour integrals. So first of all, this integral was positively, I'm gonna back off of that statement. It was going like this. It had a direction it was going, right? And if we were to complete that path, it would eventually, if we were to complete the circle around, it would be positively oriented. But it was starting down there and going down there. I'm going to define negative c to be the path, and this is in quotes there. You can't actually take a negative of a path, but this is going to be a symbol for the same path gone in reverse. Like that. Okay, so let's see if we can compute this integral really quick and just see what it was. So remember, this integral here, it was equal to I pi. Okay, so let's see what it is when I go in the negative direction. So again, z of t, now we can write that as e to the negative I t. That will do it for t going from pi over 2 all the way to, negative pi over 2 all the way to pi over 2. Okay, so that again, we'll start up there and we go down to here. Okay, so just like before, z prime is equal to negative I e to the negative I t. All right, we'll put it all in then. That becomes negative pi over 2, pi over 2. And we have now, if I take the bar over that, it gets rid of we take the complex conjugate, it becomes e to the it, and then we have negative I times e to the negative I t dt, and we see we get a similar integral as before, but it's actually negative, so that becomes negative I pi. Okay, so again, it's an opposite sign of this, so it turns out this is always true. And TRUE. So what I mean by always true is taking path in opposite direction direction changes sign of the integral. So we have a symbol for that. We write it as this. If I take, and that's what I mean by negative c, right? If I take this path, the negative path, it's the same as taking the positive path, but assigning a negative sign to. So what you might want to do then is, depending on convenience, you may want to, because it's easier to compute one way or the other, it's more conceptually simple, and then you can always just take the negative at the end if you want it going the other direction. So this turns out to be just a nice convenience formula if you're taking integrals. So perhaps you want to take this integral, but it's just conceptually more simple to go in the opposite direction. Just slap a negative sign when you're done, and it's the same as doing that. Okay, so now let's use this idea and do one more example computation, a more involved one. Okay, so let's talk about doing, we're going to talk about this function now. F of z is equal to y minus x, that'll be the real part, minus I 3x squared. Okay, so again, our z is going to be x plus I y. All right, and we're going to take it on this path. I'm going to write this path as follows. We're going to do a triangle in the complex plane. Okay, there's x, there's y, and right there that is going to be 0, comma I, and that's going to be 1 plus I, this point right there, and that's going to be 0, 0, okay, the origin. All right, and I'm going to go around this path. It's going to be a simple closed contour. It's not differentiable because there's these points, these edges there, these corners that, but there are segments that are certainly differentiable. Each line segment connecting these points is, so I'm going to call that my C, and I'm going to label this as these vertices here as that's going to be A, this is going to be B, and that's going to be, well, I really shouldn't have used that. I'm not going to call it, this contour now will be called D. I'm going to call that vertex C. So I want to integrate d of f of z dz, and now I know this is going to be equal to integral of ab f dz plus integral of bc f dz plus integral of ca f dz, where these symbols now represent the respective line segments AB, BC, and CA. Okay, all right, so we've broken up into 3 pieces. Now let's do those 3 pieces separately and then add them up to get our full result. Okay, so let's try that. So let's try AB first. So AB travels, I can write this. So this will be the AB integral. And that goes z of t is actually equal to t plus I of t. And we're going to take t running from 0 all the way to 1. And that certainly does trace out this path from 0, 0 all the way up to 1 plus I. That definitely gives it to us. And of course, we need to break it up. We need to do what we normally do with this, which is, okay, so this is my x of t, and that is my y of t. All right, and so we're going to have to plug those in to this function up there. We also have to write z prime of t is equal to going to be 1 plus I when we take its derivative. All right, so let's see if we can do this down here. So that becomes the integral AB, this one right here, becomes 0 to 1. And now we have to, so the y value is t, so that becomes, I have to put it in there, so here's the y value, that becomes a t minus t, right, minus I, 3, and then here I put a t in there, right, because that's what we have here, okay, so that's a t squared, good, and then we have to multiply by z prime, which is going to be 1 plus I dt. Of course, that part goes to 0, and then we have a negative I 1 plus I, and those are all constants that we can factor out, and that's 0 to 1. And then we have a t squared dt, which is equal to negative I plus 1 times, so there's a 3 sitting there, and that becomes t cubed 0 to 1, which becomes 1 minus I. Okay, so that was the first integral. Now I'm going to carve out some more space to do the other 3. Okay. So our first result was we computed this one. Now this one we can do it that way, but we see it's kind of going right to left. I might want to actually go left to right. So what I want to do is reverse the polarity. So we have this integral going BC of f dz. I'm going to do this to be the negative one as CB of f of z dz. I'll just reverse that polarity by slapping that negative sign on there. In which case I have z of t is equal to t, which is the x value, and it's going along there, but it's up at I, right? So we're going to go plus I, and that gives us a way to write this path, this contour here. And that's over, that's going 0 to 1, okay, in which case we can write z prime is equal to 1, right? And then we can write this integral as 0 to 1, and then we have to put our value in there. So we have the y value is I, and then we have a minus t, and then that's the first input. And the second input is minus I 3 t squared, and then we have to multiply the whole thing by z prime, which is 1, times dt. Okay, now we're going to integrate this. We have an I t minus t squared over 2 minus I t cubed, all evaluated at 0 to 1. And we get, coming out of here, pretty simple to see, that's going to be I minus 1/2 minus I. Okay, so looks like I might have a mistake in here. Let's see if I do. Well, that looks I found my mistake. We need to input y, not iy, into that, so that just becomes a 1 there, okay? And so that becomes a 1 too, and that becomes a 1 as well, right? In which case we get 1/2 minus I. Okay, so that was my mistake, is when I put y in there, I thought it was iy I need to put in there, but it was actually just the value 1, because that's what the value of y of t is. Okay. All right, so there is the value here. But the next thing we need to do, remember, is then we needed to put a negative sign on everything. All right, so that actually, we have to put a negative sign on the whole thing, like that, and we get actually out of it I minus 1/2, because we did the integral in this direction, but we need to then reverse that polarity. We need to go back the other way. All right, so that's that computation. And then finally, the final computation then is going to be, we're going to do the same thing. We're going to start down at the origin and go up and then take the negative. So now integral of AC is going to be equal to, of f of z dz. It's going to be integral from 0 to 1. And I'm going to take z now to be, it's going to be it going from 0 to 1, and that means that this is going to be 0 plus it, so that'll be my y value, and then my x will be this, so I'll have a t there minus 0. Okay, I'm just evaluating our function here now, and then it's going to be a minus I3 times 0 squared, d. And then the next thing we need to do is, of course, take our z prime, which is going to be I. So we have to multiply an I outside of everything, dt. All right. So, sorry I'm running out of room here, but that's clearly going to be t squared over 2, evaluated, or times I, evaluated at 0 to 1, and that's going to be I over 2. But remember, that was the integral from a to c, but we wanted to go the opposite direction, so we need to put a negative sign on everything, and that becomes negative I over 2. So, to conclude, let's see if we can keep this all on one page there and put all of our pieces together. What we have is, that's going to be, our first result was 1 minus I. That was the integral from a to b. And then the second piece was plus I minus 2. And then finally a minus I over 2. And that in toto is equal to 1 minus I over 2. Okay, so that's our result from doing our integration through all those pieces, and hopefully that gives you a good grounding on how to compute contour integrals in a plane. One thing to note is that as we went around this circle, we actually got some non-zero integration out of it. The result of the integral was non-zero. So one thing to note is that, of course, this integral here, and if I were to reverse polarity and go that way, I would have integrated to both pieces. So let's just study that really briefly. So we had here the integral going along this curve here was equal to 1 minus I over 2, and that was integral of c f of z dz. And what we had was the a to b integral. That was equal, so I'll call that I a to b. That was equal to 1 minus I. Okay, so the next piece there of this puzzle then is, if I take now the integral here, if I want to go a to b a different direction, I want to go a c b, right? I a c b. That means going this way and then that way. Well, that means I take the negative of the two other results we had, and the other result was the BC result. If I take the negative, that was an I minus 1/2. Then I'm going to take the negative of that, and I'm going to add it to, of course, also, so that was the BC path. And then I have to, the AC path was the same thing. It was plus, it became a plus I over 2. So what we see there is we got 1/2 minus I. Oops, I'm making a mistake here. Let's just back up there a second. What we had there now is we need to put a negative sign there. So that was our, so this was I A C, and that is our integral I C B. And those become, I'll rewrite this down here, that becomes 1/2 minus I over 2, and that becomes 1/2 minus 3I over 2. So what we see here is integral from here, from A to B along this arc here, produced a 1 minus I result. But if I take a different path, I should say, that leads to the same point, I got a different result here. So this is an example of, at least with this particular function that we picked, f of z, we got two different results depending on path. So we say the integral from A to B depends on path you choose. So it will turn out there are some very important functions out there that are independent of path. But we'll cover those in another video. So thank you very much. Sorry, I wanted to holler at you before you leave. I made a mistake on my signs here. It turns out that, pardon me, integral AC, that's going to be equal to the value I over 2, and the integral CB is equal to 1/2 minus I, the sum of which, if I add these two together, is going to be equal to 1/2 minus I over 2, which of course is not equal to 1 minus I. So again, the integral from a to b does depend on path. You don't get the same result if you go on different paths. But I did do my arithmetic wrong. So this is the correct result, but although the result in terms of dependence of path is the same. So thank you very much.